we have been discussing the derivation of continuity equation, and from the continuity equation the related items that we define and that they generate from there are things like stream function, the potential function, and the different parts of vector properties that are standard properties that we use in the definition and application of Navier-Stokes equations. So all these equations we have discussed. Particular importance are conservation of mass, the continuity equation, derivation equation using the divergence theorem. This has also been derived by using infinitesimal control volume and similarly alternate forms of continuity equation. And from this we derive functions like psi. You will recall that psi is a function that we define from the continuity equation such that this function will satisfy the continuity equation. The continuity equation is divergence of v is equal to 0, in which the u is defined as d psi partial differentiation of psi with respect to partial differentiation of y, and v is the partial derivative of psi with respect to x. If I substitute it back into the equation, you will see that this will identically satisfy the equation. So similarly, the related items, the differential linear momentum equation, the Cauchy's equation, and they have been derived using different techniques. Particularly among them, one of the important and standard ones is using Newton's second law of motion, which is used in classical mechanics as well as in fluid dynamics also. And then we discussed some of the parts of Navier-Stokes equation, the difference between the Newtonian and non-Newtonian fluids. Similarly, their properties, what happens if they are incompressible, if they are not incompressible, if they are continuous, if they are not continuous, and those kind of things. Then, of course, the Navier-Stokes equation, what happens if we use them in rectangular coordinates, and what happens if we use them in polar coordinates. And when we say polar coordinates, we mean if the geometry of the fluid that is taking place, fluid flow, is in cylindrical motion or cylindrical setup, then we choose the cylindrical coordinates rz or r phi z. And similarly, if it is a spherical geometry, then we use spherical polar coordinates r theta phi, and so on. So these are standard things that we discuss, and we are going to treat some more solutions of Navier-Stokes equations by using a bit of detailed mathematics as well as different aspects of this equation, in which the standard exact solutions are discussed. Remember, I have mentioned this and we know it, that Navier-Stokes equation is a difficult set of equations to solve, analytically incomplete. This is because the equations are by nature nonlinear. So, however, under specific conditions and under specific boundary conditions, there are few cases in which exact solutions can be found, and they are standard setups. They are normally discussed in a course like the one that we are having now. So a little more mathematical treatment under different aspects, and we are going to discuss them, some of these cases.